feels like this is someone's idea of a sick joke, but here are the answers. This is the original function f of x. This is using the Desmos derivative operator to find the derivative of that function. And then down here, g sub 3 of x is the simplest form for the derivative. And if I go to Desmos, sharing my screen, and I highlight the derivative with respect to x, I'm sorry, the derivative of f of x as g of x, and highlight g sub 3 of x, that kind of proves that they're the same because the functions, the graphs overlap each other. And similarly for y double prime, there's y double prime, and there's the answer that I got, and they overlap each other. So that kind of proves that these answers are correct. The question is, how did I get them? And we're not going to go through it all, but you have three choices. You can use the product rule, because this is the product of two functions, which will require the power rule and the chain rule for each term of the derivative. You can use logarithmic differentiation, which is what I'm showing here. Or you could actually expand each of these binomials using probably the binomial theorem and then differentiate term by term. That might actually be the easiest. But if I take the derivative, take the logarithm of both sides, ln of both sides, I can use the properties of logarithms to rewrite the log of this mess right here as, well, the logarithm of a product is the sum of the logs, and then the power property of logarithms allows me to pull the exponent down front. So I took the derivative of this first term here by taking 3 times the derivative of 2x squared plus log of 2x squared plus 5x is 1 over that, times the derivative of the inside. That's the chain rule. So now I'll continue here to show you how I would be doing this. I'm taking 4 times the derivative of ln of x squared minus 1 is 1 over x squared minus 1. And then multiplying by the derivative of the inside, which is 2x. Okay, and now y prime equals, I'll simplify each side, 12x plus 15 over 2x squared plus 5x. And I'm going to put this whole thing in brackets. You'll see why in a second. 8x over x squared minus 1. But now I have to multiply both sides by y in order to isolate y prime. And y is 2x squared plus 5x, quantity cubed, times x squared minus 1 to the 4th power. And if I actually distribute these two binomials over the brackets, well, the whole idea is that when I take these two binomials times this first term, this 2x squared plus 5x in the denominator cancels out. So I get 12x plus 15 times 2x squared plus 5x. Instead of cubed, I'll have squared because one of them canceled out, times x squared minus 1 to the 4th power, plus 8x for this term. None of the 2x squared plus 5x's cancel out. So I've got cubed, and then one of the x squared minus 1's cancel out, leaving me cubed. Now, what do you do from here? Well, probably the easiest thing to do is to factor out the greatest common factor from each of these terms. So I see a 2x squared plus 5x squared quantity squared. I see an x squared minus 1, the quantity cubed. And now what's left inside from each term? Well, I've got a 12x plus 15. I've got I factored out all of these for both of those, but I've got an x squared minus 1. And I ran out of room here, so I'm going to just put a plus sign here. That's for this term here. I've got an 8x times 2x squared plus 5x. And now we can multiply these two binomials together, combine similar terms, and we'll have that third term, okay? And now you have a product of 3 factors, and you can continue with logarithmic differentiation by taking ln of both sides and doing this kind of thing right here on the second derivative, which is what I did on the Desmos screen that you saw on board 1. Wow, what a mess. I will send the link to this Desmos graph so you can take a look. There you go. Hope that gave you some idea how to proceed.